The D block of the periodic table begins with a single foundational column. Group 3 serves as the entry point to the transition metals, establishing the chemical baseline for the elements that follow. The first two positions in this column are consistently occupied by scandium and yttrium, with atomic numbers 21 and 39. In their pure forms, these are soft, silvery white metals. They share a highly specific set of behaviors that define the criteria for Group 3 membership. The structural conflict arises immediately beneath them. The identity of the elements occupying the third and fourth slots of this group has been a subject of long-standing discrepancy. Open a standard chemistry textbook from the late 20th century, and you will likely see these positions filled by lanthanum and actinium. This specific arrangement, scandium, yttrium, lanthanum, and actinium, was established in educational curricula before advanced structural chemistry could accurately map the quantum behavior of heavier atoms. Relying on this legacy layout misrepresents the actual quantum mechanics of the D block. The physical evidence dictates a revised sequence for the heavier members of the column. Modern structural chemistry, supported by the International Union of Pure and Applied Chemistry, has moved to correct this map. The third member of Group 3 is lutetium, atomic number 71, and the fourth member is the synthetic element lawrencium, atomic number 103. Displacing lanthanum and actinium from these slots is a necessary scientific correction based on observable physical evidence. To prove that lutetium and lawrencium belong in these exact positions, we examine two primary mechanisms: the uniformity of their +3 oxidation states and the phenomenon known as the lanthanide contraction. Understanding the shape of the periodic table requires looking past legacy diagrams to observe how these elements interact in a reactive environment. Compared to heavier transition metals like iron or gold, Group 3 metals are highly electropositive. They readily surrender their outer electrons. On a macroscopic level, this high electropositivity means these metals tarnish almost instantly. In ambient air, pristine surfaces degrade into a powdery crust. They react aggressively with water, rapidly shedding electrons in a chemical exchange that breaks apart H2O molecules. The specific mechanism driving this reactivity is the element's ability to reliably shed exactly 3 valence electrons, forming a +3 oxidation state. This ability to form an M3+ cation is the defining functional signature of the entire group. Scandium and yttrium exhibit this +3 behavior, establishing a strict chemical test that any heavier element must pass to occupy the slots below them. Any element claiming a position in Group 3 must mimic this exact electropositive M3+ cation forming profile. Returning to the periodic table, we encounter a structural anomaly when we move from yttrium down to lutetium. The numerical gap is substantial. At atomic number 71, lutetium has nearly double the atomic number of yttrium at 39. Physically, this means lutetium possesses an additional 32 protons in its core, surrounded by an additional 32 electrons. Basic atomic logic suggests that adding 32 extra protons and several new electron shells should result in a significantly larger atomic radius. Yet, despite the addition of subatomic particles, lutetium's atomic radius is practically identical to yttrium's. This size parity creates an unusual situation, a heavy element mirroring the physical dimensions of a much lighter one. The explanation requires looking closely at the quantum mechanics of the shells themselves. The physical paradox of lutetium's size is governed by a quantum mechanic known as the lanthanide contraction. Before reaching lutetium, the periodic table fills an entire row of inner F-block elements, the lanthanides. In atomic physics, inner electrons normally provide electron shielding, creating a barrier. This barrier blocks the strong positive pull of the nucleus from reaching the outermost electrons. But the 4 F electrons added during the lanthanides core shielding against the positive charge of the growing nucleus. As a result, the positively charged nucleus overpowers this weak F-block shielding, pulling the outermost electron shells inward. This inward pull negates the expected size expansion from the 32 additional protons. Because lutetium and yttrium share the same radius, they interact with other molecules in identically spaced chemical environments. The lanthanide contraction forces lutetium to match yttrium's +3 valence behavior and physical dimensions. This data confirms lutetium as the correct successor in group 3. The uniform +3 oxidation states and tightly constrained atomic radii of group 3 elements make them critical in advanced engineering. When alloyed, scandium's unique reactivity and incredibly low weight combine to create high-performance metals utilized in modern aerospace fuselages. Yttrium's predictable +3 oxidation profile is used for synthesizing the red phosphors that illuminate modern LED screens. Lutetium, with its mass packed into a constrained atomic radius, acts as a specialized catalyst in industrial chemical processing. These technologies rely on material scientists understanding the precise atomic behaviors and dimensions that define the specific column of elements. The periodic table is a map defined by strict mathematical and physical laws. Placing lanthanum and actinium in group 3 ignores the reality of the d block and the effects of f-orbital shielding. Scandium, yttrium, lutetium, and lawrencium are the only elements possessing the correct physical dimensions and reactivity to occupy the first column of the transition metals. Correctly identifying these elements allows us to accurately predict the reactivity and structural properties required for advanced materials science.